So in the last class, what we have seen in the last class, we seen about this. What we have seen?
Non-linear region.
MOSFET in non-linear region and non-linear region. No. Okay.
Non-linear.
Okay. Today we discuss about the operation of MOSFET in saturation region. Okay. Saturation region. Okay. Operation of enhancement MOSFET. Operation of enhancement MOSFET. One second. Yeah. Operation of enhancement MOSFET. Enhancement MOSFET in saturation. Okay. In saturation region. Okay, so what is the condition for this saturation region? So condition for this saturation region is VGS is greater than VT. VGS is greater than VT, and you are increasing more and more VDS. Okay, you are increasing more and more VDS. So VDS is more value. Okay, and such a way that yesterday we discussed about pinch off point. No, what is the pinch off point? So what is the condition for pinch off point? Pinch off condition. We already seen that is VDS,
So
that is equal
VGS
to what?
equals to VGS minus VT.
VGS minus VT. VGS minus VT. Okay,
VT.
so it means pinch off point is means it reached the pinch off point, and you are increasing VDS such a way that VDS is greater than or equal to VGS minus VT. Greater than or equal to what? VGS minus VT. Okay, so VGS is greater than or equal to VGS minus VT. Okay, so what happens when it is greater value? So here I will draw this MOSFET in saturation region. So here if you see, so this is n plus. Okay, this is n plus, and this is n plus p substrate. Here we are giving VSB equal to 0, and we have oxide layer, and next we have polysilicon. Okay, and above this there is a metal. So source is connected, this is source is connected to ground, and VGS is connected to positive. So VGS is with respect to source, you are giving this is VGS. VGS is greater than VT. Okay, positive and negative. VGS is greater than VT. This is gate, and next here you are applying VDS. Okay, VDS such a way that so what is this VDS? VDS is greater than 0. Greater than 0. Okay, so what happens as VDS? So that means here you are increasing. So that means first you are making what for channel formation, VGS is greater than VT, and we are making as constant. So next what we are doing, we are increasing the VDS more and more. So VDS you are increasing more and more such a way that VDS is what? VDS is greater than or equal to what? VGS minus VT. Okay, so VGS minus VT, what happens? There is a non-uniform channel. Non-uniform pinched off channel. Okay, there is a non-uniform pinched off channel. Pinch off channel. So channel will be what? So that means this channel normally it will come like this. It will come like this. So it will come towards source side. Okay, towards source side it will come, and there is a non-uniform pinch off. So this is nothing but we call as a pinch off point. Okay, pinch off point, and this is nothing but induced channel, no? So internally developed channel. Okay, so that means further increase in VGS. If you increase further increase in VGS, what happens? The pinch off point moves slightly from the drain to source. Okay, so whatever the pinch off point is there, okay, pinch off point, slightly move towards, move from where to where? This is drain, no? Drain to source, drain to source. Okay, so that means here, as you increase VDS, incremented in VDS, there will that will be appears across depletion region. So there will be a depletion layer. Last class I told you there is a depletion layer. So depletion layer will increase. Okay. So depletion layer will increase, and here the pinch off point will be moved towards this region. Okay, pinch off point will be moved towards this region. Okay, so that is nothing but such. So normally the ID current, drain current should becomes constant, but ID current is not making as constant. It is ID current, it should be zero. Okay, it should become zero, but ID current is not making as zero. There is some amount of path will be there. Due to that path, there is a constant in ID current. Okay, so constant in ID current. So that means VGS is greater than VT, and VDS is more value. Okay, so VDS is more value, greater than 0, and VDS is greater than or equal to what? VGS minus VT. VGS minus VT. Okay, so what happens here? As VDS is more value, so as VDS, this is the condition for saturation. As VDS is more value, okay, more value, such a way that VDS is what? Greater than, VDS is greater than or equal to VGS minus VT. So what happens? There is a drain current which is constant. There is a drain current, which is what? ID becomes constant. Okay, ID becomes constant. That is due to velocity saturation. Velocity saturation. Some amount of charge carriers will move from where? What are the charge carriers? Electrons. Okay, due to velocity saturation, some amount of electrons will be moved from where to where? Source to drain. Okay, due to this velocity saturation, what happens? There is a current will be there. That current is constant. Okay, so if you draw the characteristics, ID with respect to VD, so ID, so this is ID with respect to VD, so VDS, this is VDS, and this is ID. Okay, so we already seen, that means first this is nothing but cutoff region. This is nothing but cutoff region, and here this is linear region. After some point, what happens? So it will converted the rate at which the drain current will decrease. The rate at which, that is non-linear region. Okay, this is linear region, and this is non-linear region. And after that, here you will get a pinch off point. This is nothing but VDS sat. This is equal to what? VGS minus VT. After that, the drain current become constant. So this is nothing but what? Whenever the drain current become constant, that is nothing but we call as saturation region. Okay, so this is about the saturation region. Any doubt in this saturation region? Yes, shall I move forward?
Sir, can you explain this once again after this non-linear pinch-off condition?
Non-linear means here what happens? In the non-linear, I told you, no, non-linear in nature. So what happens? In the last class I told you, channel becomes non-uniform. So channel becomes what? Non-uniform. Okay,
Not
non-uniform. So non-uniform. So that means if you draw like so this is the n plus, and this is the n plus, and this is p substrate. Okay, and SiO2 layer, and next this is polysilicon, and metal. Okay, so in in non-linear region what happens, channel initially linear region channel is uniform. Okay, linear region channel is uniform, it is acting as a resistor, that's why you are getting what, linear region, you are getting linear region. After
Yes.
that what happens, here, so due to increase in VDS, the depletion layer will increase. Okay, so that means potential difference also increases. So that the last class I told you, there is nothing but VGC equal to VDS minus VT, I told you. Okay, so VDS minus VT, this is VGS minus VT, some condition I told you, no. So what happens here, the potential gate to channel potential increases. Okay, so gate to channel potential increases means here, this becomes what, non-uniform, this becomes non-uniform. So if you goes on decreasing, increasing VDS, so channel will be coming towards which region means, this is source and drain and next gate. Okay, so at one point, so channel will decrease, so gradually it will decrease. Okay, so drain current will increase, drain current will increase, the rate at which the increase in the drain current will decrease. Normally how it should increase, like this it should increase. Okay, but the rate at which the drain current will decrease. Okay, at one point what happens, channel will be, so the channel depth will become 0, channel depth becomes what, 0. Okay,
Zero.
channel depth becomes 0. Okay, further increase in VDS, this you are increasing VDS is nothing but you are increasing the reverse bias voltage. Okay, reverse bias voltage, further increase in if you increase the reverse bias voltage in the PN junction diode, we already seen. So if you increase, so this is P and this is N, for the reverse bias, what we have seen, we applied the negative to P side and positive to N side. As you increase more and more this voltage, what happens to depletion layer, depletion layer increases, no,
Yes.
depletion layer also increases. So same like this, if you increase, so depletion layer will come towards this channel. Okay, that will eat away this channel. Okay, so what happens, when you increase more and more, so pinch off condition is occurred. What is the pinch off condition? This is pinch off condition. After that, after pinch off condition, means you are increasing VDS, that is more than VGS minus VT. So channel will be channel is going towards, from the source end to drain end. This is nothing but we call as punch through or reach through, punch through, punch through, or we can call as reach through, reach through. Okay, reach through. So here what happens, gradually there is no path is there, but due to some velocity saturation, due to some electrons, charge carriers will move towards this path. So what happens in the saturation, the drain current, gradually it is converting non-linear to constant, non-linear to constant. This is nothing but drain current is constant, ID becomes what, constant in the saturation region. Is it fine?
Yes, sir.
Okay, so this is about the, so all regions we discussed. One is what, cutoff region, this is cutoff region. Okay, so cutoff region, so what is the cutoff region, VGS equal to 0 and
Zero.
VSB equal to 0 and VDS equal to what, 0. Okay, there is
Zero.
no drain current, ID equal to 0. Okay, and linear condition also we already seen. What is linear condition? VGS is greater than VT, and tell me, VDS is small value, and VDS is less than
VDS is less than
VGS minus
VGS.
VT. Okay, this is linear region. And what is non-linear region? Non-linear region is VGS is greater than
VGS is greater than
VT,
VT.
channel formation, and VDS is more value,
VGS is more
more value,
zero.
and VDS is what, VDS
VGS
is less than VGS
less
minus
than
VT,
VT.
VGS minus VT. So what is saturation region? VGS is greater than
VT.
VT and VDS is more
VT is more
value,
than
and VDS
VDS
is greater than
greater
or
than
equal
equal
to
to VGS minus VT.
VGS minus VT. VGS minus VT. Okay. This is pinch off point. Anyway, what is this pinch off point? All cases are same. VDS is equal to VGS minus VT. Channel will be pinched off. Okay. Channel depth becomes 0. Yes. Is it fine? All the conditions and all the regions of operation?
Yes.
Okay. And next we will see the drain characteristics. What are the drain characteristics? We will see. Okay. So drain characteristics, if you see, drain characteristics of enhancement MOSFET. Drain characteristics of enhancement MOSFET. So here what happens? Drain characteristics is nothing but I am drawing ID with respect to what? VDS, no? This is nothing but drain characteristics. Okay, ID with respect to VDS. Okay, so here drain characteristics will be like this. So like this drain characteristics will be. Okay, so that means till here to here this is linear. Till here to here this is linear. From here to here this is what? Non-linear. And from here to here this is what? Constant. Constant. Okay, so that means from here I can write so here this point, what is this point? So almost a straight line with slope proportional to what? VOV. So almost straight line, linear region, no? This is what? Linear region. Okay, so linear region, straight line, channel is acting as a resistor. Okay, straight line with slope. What is the slope? So with the slope proportional to VOV. That is nothing but overdrive voltage. Okay, and next this is what? Non-linear region. Non-linear region. So this non-linear region, what happens? The curve bends. Okay, the curve bends. The curve bends. Why it is bending? Because the channel resistance, whatever the channel resistance is there, that channel resistance increases with VDS. Channel resistance increases with VDS. Okay, so here both this linear region and non-linear region, I can say this is a triode region. What is this region? Triode
Trial.
region. Triode region. Okay, so triode region, when you will get when VDS is less than or equal to VOV.
Three.
What is VOV? VGS minus VT.
Overdrive.
Overdrive
VGS
voltage.
minus
VGS minus VT.
three.
Overdrive voltage. I already told. Overdrive voltage equal to what? VGS minus VT. So if you see the conditions, that means linear region and non-linear region, you are getting when VDS is less than VGS minus VT. See here also VDS is less than VGS minus VT. Pinch off point VGS equal to VDS equal to VGS minus VT. So from this I can say that triode region is nothing but this is VDS sat. This is nothing but VDS sat. VDS sat. VDS sat is pinch off point. This is what? VGS minus VT. VGS minus VT. Okay. So both linear region and non-linear region we call as which region? Triode region. Okay. And this is saturation region. This is what? Saturation region. Saturation region. Okay. So saturation region means what? So at the saturation region, the current saturates. Current saturates. Current saturates means what? Current becomes constant. The drain current becomes constant or constant. the drain current becomes constant, okay, because channel is pinched off at the drain end, because the channel, whatever the channel is there, channel is pinched off at the drain end, at the drain end, okay. So with the channel is pinched off, there is like whatever the drain current is there, VDS no longer affect the channel, okay. VDS no longer affect the channel, no longer affect the channel. So that means further increase in VDS, the channel means channel is pinched off, the drain current becomes constant only, okay. When it is constant, now drain current is depending on which one, means during the saturation condition, drain current is depending on VGS, drain current is depending on VGS, okay. So these are the regions, okay, non-linear region, linear region, non-linear region, both we call as triode region, and these are the conditions, and saturation region, okay, saturation region. So here I can write VGS equal to what, VT plus VOV, VT plus VOV, okay. This is also called as overdrive voltage, VOV. This is the drain characteristics. Did you understood?
Yes, sir.
Yeah. Now you see. So the detailed drain characteristics next I will draw. Okay. So like MOSFET, MOSFET. Suppose if you consider BJT, BJT have what characteristics? Input characteristics and output characteristics. But MOSFET doesn't have the input characteristics. MOSFET have which characteristics? Can anyone say? MOSFET, so that means if you see the MOSFET diagram, so you have like you have insulator in the gate. Insulator in the gate means high impedance will be there, okay. So that means nearly the gate current is what? Gate current is 0 only, okay. Gate current is 0 only. When gate current is 0, you don't have what? You don't have input characteristics, okay. Whereas in BJT you have input characteristics, but in MOSFET, you have which characteristics? Means transfer characteristics. Transfer characteristics. What are transfer characteristics? That means VDS, the output voltage, versus sorry, not VDS. One second. Input voltage. What is the input voltage? VGS. VGS versus output current. What is the output current? ID. That is nothing but transfer characteristics. Okay. From the drain characteristics, from the drain characteristics, you'll get the transfer characteristics. Okay. You'll get the transfer characteristics. That how you are getting, I will tell you. Okay. So see here. So I will draw the drain again. I will draw the drain characteristics. Again I will draw the drain characteristics. Now you understood MOSFET, why the MOSFET doesn't have the input characteristics, okay. So that means it is having high impedance. Why? Because oscillator is there, sorry, insulator is there, okay. Silicon dioxide is there at the input, okay. So that's why due to that insulator, the gate current is nearly 0, okay. So for that you have transfer characteristics, that is nothing but input voltage with respect to output current. Input voltage with respect to output current, that is nothing but transfer characteristics. So how we are getting, I will tell you. So just I am drawing the drain characteristics. This is nothing but drain characteristics. So this is what? This is ID with respect to what? VDS. ID with respect to VDS. Okay. So here so how many regions are there? One is cutoff region, no? So cutoff region means here this is cutoff region, okay. This is cutoff region. So what is the condition? VGS is less than or equal to VT, okay. So this is cutoff region, okay. And next you have different value, at different value of VGS, there are different value of currents are there, okay. So I told you, in saturation the output is depends on what output current, the current is depending on VGS, no. So here I can write, so I can draw like this. So I can draw, so this is what, this is VGS equal to VT plus overdrive voltage VOV1. Okay, next, this is one more curve, uh, VGS equal to VT plus VOV2. Okay, and next we have like this, VGS equal to VT plus VOV3. Okay, and next you have this is what, VGS equal to VT plus VOV3. Okay, so that means I told you, like, what is the locus. So this is like, if you consider, this is the locus, this is the locus point. Okay, so this is the locus point. If this is the locus point, from here this is triode region. Okay, so this is triode region. What is the condition? VGS is less than or equal to one second, VDS is less than or equal to VGS minus VT. Okay, and this is all, this is saturation region. Okay, so saturation region, the channel nowhere, means, if you vary some voltage, VDS, the channel is nowhere depending on VDS. So where it is depending means, for different values of VGS you will get different values of ID current. Okay, so here this is VDS is greater than or equal to what? VOV. VOV means what? VGS minus VT. Okay, so this is saturation region. Okay, so if you combine this, locus points towards this side, and here I am considering as VGS. Okay, so if you combine these locus points, so here I am combining, and here I am combining, and here I am combining, and here I am combining. So if you draw the curve combining these points, okay, these points, you will get which curve? Transfer characteristics. What are transfer characteristics? That is nothing but VGS versus ID. VGS versus ID, that is nothing but transfer characteristics. Did you understood how I am drawing the transfer characteristics? Okay, so here if you see, so that means, if you draw the separately the transfer characteristics, so transfer characteristics, so so here I am drawing the transfer characteristics. Here what happens, till VT there is no current, channel is not forming. This is in which region? Cutoff region. Okay, so that means here ID. Okay, so this is VGS with respect to ID. Okay, so ID is 0. For which condition? VGS is less than VT. So when VGS is less than VT, there is no channel formation. Means what? It will be in cutoff region only. There is no drain current. Okay, it will be in cutoff region only. Okay, so what happens? Again it will increase. Okay, again it will increase like this. Okay, again it will increase like this. Okay, so ID increases with VGS. ID increases with what? VGS. So what we did, so that means VGS VGS is what greater than VT, channel is forming, and VDS we are making as 0. We are getting it linear region, no? Somewhere here you will get the linear region. Okay, somewhere here you will get linear and linear region. So let us take this is linear region, and next from here to here you will get a non-linear region, and this one is saturation region. This one is saturation region. Okay, so as you increase VDS more and more, okay, so that is VDS is greater than or equal to VGS minus VT. VGS minus VT. Okay, so the in this position, that is saturation region, ID depends on what? ID depends only on VGS. Only on VGS. Okay, so this is the condition, means in saturation condition, this is saturation condition, VDS is greater than or equal to what? VGS minus VT. You need to understand that conditions. Okay, you need to understand this condition. So this is the transfer characteristics. Any doubt in this? Shall I move forward?
Yes.
Anyone? Waiting for your response.
Yes, sir.
Okay. So this is about the characteristics, drain characteristics, transfer characteristics, all those things. Okay. And next you see. So next, drain current equations in enhancement MOSFET. Okay. What are the drain current equations? Okay. So if you see the drain current equations, drain current equation. Drain current equation of enhancement N MOSFET. Okay, N MOSFET. So here you have what is the first region? Cutoff region. What is first region? Cutoff region. So what is the condition? Condition for cutoff region. Condition for cutoff region. Here VGS is less than VT. VGS is less than VT. In cutoff region, is there any drain current? No. IDS equal to what? 0. Okay. IDS equal to 0. Okay. And in linear region, VGS is greater than or equal to what? VT. Okay. And VDS is less than VGS minus VT. Okay, so what is IDS? IDS equal to mu n COX. Okay, mu n COX. 1 second. The IDS current is mu n COX W by L VGS minus VT into VDS minus VDS square by 2. Okay, so here this is the condition, means the derivation is there, derivation is not required, just you need to remember the drain current equation. Okay, so what is mu n?
Mu n after mu n.
Something you are asking?
Yes, sir.
What you are asking?
So what is it after mu n?
Mu n COX. Mu n is nothing but what? Mobility. Mobility of what? Electron. Mobility of electron. We already seen in the semiconductor physics, no? Mu n is the mobility of electron, mobility of hole. Okay, that we have seen in the semiconductor physics. Okay, as this is n channel, so in the channel, the what are the charge carriers? Electrons are the charge carriers. That's why mu n is the mobility of the electron, and COX is nothing but oxide capacitance. Which oxide you are using? SiO2, no? Silicon dioxide. Where it is there? Silicon dioxide. Above the gate, silicon SiO2 is there, no? Above the silicon, when I drawn this, this is nothing but what? SiO2 layer. This oxide capacitance, COX. Okay, COX, and next W by L is there. W by L is nothing but what? W by L is nothing but aspect ratio. W by L. W by L is nothing but aspect ratio. Aspect ratio. Aspect ratio. That means width of the channel and length of the channel. So if you see the three-dimensional view of this MOSFET, there will be width also. I shown the two-dimensional view. Two-dimensional view you can't see the width, but in three-dimensional view you can see the width. Okay, so width by length of the channel is nothing but aspect ratio. So basically I told you know that technology. So technology, nanometer technology. We are in we are working with 17 nanometer technology. So that technology is nothing but that the distance between source and drain. That is nothing but technology. Now we came up with the 2 nanometer technology. No, now we making the chips with 2 nanometer technology. Okay. So and VGS, you already know all these terms. VGS is gate to source voltage, and VT is threshold voltage, and VDS is drain to source voltage. Okay, drain to source voltage. Now if you see the saturation region, saturation means just I will tell you, uh, when you get the saturation, when VDS is greater than or equal to what, VGS minus VT, no, VGS minus VT, then the saturation will come. Okay, so just I am substituting this VDS equal to VGS minus VT in the above equation. Okay, so if you substitute, what you will get, IDS equal to mu n COX W by L. Here what you will get, VGS minus VT into VGS minus VT minus VGS minus VT whole square divided by 2. Okay, so this is 1. Okay, so if you take LCM, what you will getting, mu n COX W by L. Here you will get it 2 into VGS minus VT whole square minus VGS minus VT whole square divided by 2. Okay, again 1 minus 2, what you will get, 1, no, 1 minus 2 is 1. So this is what, mu n COX W by L into VGS minus VT whole square divided by 2. Whole square divided by 2. Okay, so this is the drain current equation in saturation region. Okay, drain current equation in the saturation region. Okay, 1 second, just wait. చెప్పండి మేడం. మేడం అదే ఫ్రీ క్లాస్ అంటున్నారా? 6:15 పెట్టేసేయండి, 6:15 పెట్టండి. 6:15 పంపేసి. ఓకే. Okay, now you see. So what is saturation region? Saturation region. So that is, in the saturation, what is the condition? Saturation, VGS is greater than or equal to VT, and VDS is greater than or equal to VGS minus VT. Now what is IDS? IDS equal to 1 by 2 mu n COX W by L VGS minus VT whole square. VGS minus VT whole square. Did you understood? Your response?
Yes, sir.
Okay. So this is about the different drain current equations in the enhancement NMOS. Okay. Now you see. So now you have two parameters. One is drain resistance and transconductance. Okay. First we will see drain resistance. Drain resistance. Drain resistance is what? Drain resistance is RD. Okay, RD equal to, you can write as dou VDS divided dou VDS by dou ID. Dou VDS by dou id. Dou is nothing but partial differentiation. Partial differentiation means id you are considering as a variable and remaining are you are considering as constant. Okay, so this I am going to derive for the id current equation in the linear region. Okay, so what is ids? Ids equal to mu n cox w by l, mu n cox w by l, and next yes, mu n cox w by l, um, vgs minus vds whole square into vds minus vds square by 2. Okay, vds square by 2. So as vds is small value, okay, in the linear region vds is small value, so that means vds square by 2. So vds square by 2 is very small value. I can neglect this. Okay, I can approximate to vds equal ids equal to what? Mu n cox w by l vgs minus vt. Okay, so this what I am doing, I am differentiating with respect to what? Vds. Okay, dou id by dou vds, this is equal to mu n cox w by l vgs minus uh, with respect to what? Dou id vds. Okay, 1 second. This one, no? RD, no? Okay. RD I am using saturation. Sorry, RD I am using for saturation. Okay. So what is saturation region? VGS minus VT. This is VGS minus VT. This is VGS minus VT. Okay. 1 second. Okay. Not like this. Sorry. Here I am going for, I am writing the equation for saturation region. Okay, I am writing the equation for what? Saturation region. So what is saturation region? So here id equal to what? Mu n cox w by l vgs minus vt into vds. Vds, this is square by 2, no? 1 by 2 will get. Okay, this you will not get. This is the equation in saturation region, no? This is the equation in saturation region. Okay, so here what you will get? So id dou id by dou vds I am taking. Okay, so dou I by dou vds equal to what? 1 by 2 mu n cox w by l 2 into vgs minus vt. Okay, vgs minus vt. 1 second. Oh, no, sorry, into vds, linear region only I need to take. Okay, linear region only. Okay, linear region only. So the differentiation of vds is what? 1, no? Differentiation of vds is 1. Okay, so here rd equal to what? Dou vds by dou vds by dou id. Dou vds by dou id equal to what? 1 by mu n cox anyway 2 is not there. Okay, w by l vgs minus vt. Okay, so this is rd. What is rd? Rd equal to 1 by mu n cox w by l vgs minus vt. From this I can say that rd, drain resistance, is inversely proportional to the aspect ratio. Drain resistance is inversely proportional to the aspect ratio. Okay, and next is transconductance. What is transconductance? So transconductance is gm is the transconductance. So gm, if you see the gm, so current by voltage is nothing but conductance, no? Transconductance. Normally resistance equal to what? V by I. Okay, conductance equal to what? 1 by resistance means what? I by V, just reciprocal, no? So that means transconductance is nothing but dou id by dou input current, input voltage, that is VGS, dou ID by dou VGS, dou ID by dou VGS. So here I am with help of this current in saturation region I am using. Okay, so what is current in saturation region? 1 by 2 mu n COX W by L VGS minus VT whole square. Okay, so this what I am doing, I am differentiating partially with respect to what VGS. I think partial differentiation you already seen, no, in mathematics. One variable you will
Yes.
that means other variables you will consider as constant. This with respect to this variable only you need to do. Okay, so 1 by 2 mu n COX W by L 2 into VGS minus VT. Okay, now differentiation of VGS is what? 1 only. Okay, so 2 get cancelled, 2 get cancelled. So what is GM? GM equal to mu n COX W by L VGS minus VT. VGS minus VT. From this I can say that GM is directly proportional to what? W by L. Aspect ratio. GM is directly proportional to, as aspect ratio increases, transconductance increases. Okay, whereas drain resistance, it is inversely proportional. It is inversely proportional means what? As aspect ratio increases, the drain resistance decreases. Okay, so this is about today's session. Yes, any doubts in this?